Hello everybody, welcome back to a second year physical chemistry lecture, and today we are going to cover the Gibbs-Duhem equation. What will be covered and why? So we're going to talk about the Gibbs-Duhem equation. This equation is most likely new to you, but this equation is a consequence of the first law, or the thermodynamic identity. And this equation is going to be important to help us understand what chemical potential is. As we go through the course, you will notice the central importance of a quantity called the chemical potential. And the Gibbs-Duhem equation is our way into it. What will you need? Well, again, you will need to remember calculus, and specifically differentiation. And the rule we are going to use in this lecture of most importance will be the product rule. So again, look up the product rule and how it behaves, and you'll understand what comes in this lecture. What else you'll need is, again, you can go to Atkinson's Physical Chemistry and look up in the index the Gibbs-Duhem equation and everything around it. Alright, a bit of history. I like history. Gibbs. Here is Joshua Willard Gibbs. He was born in 1839. He died in 1904. Was a lifelong bachelor. Worked at Yale. And Albert Einstein said of Gibbs that he was the greatest mind in American history. So let that sink in. This guy is not your run-of-the-mill scientist. Almost anything and everything to do with thermodynamics as applied to chemical systems, Gibbs had a hand. That is why we have the Gibbs free energy in his honor. He really built it from scratch. His most important work is the introduction of the concept of the free energy, which we will be using quite extensively in this course. So there's the guy. And there's, of course, Duhem, who also developed the Gibbs-Duhem equation. Pierre Maurice Marie Duhem was a Frenchman. He was born in 1861, died in 1916. And interestingly, he was a bit of a science historian and a philosopher. So you can go and read up on that. Very interesting stuff. And he also made quite a few contributions to chemical thermodynamics. And he's got a lovely beard. I wish I could grow something like that, but hey. Now, onto the nitty-gritty, the Gibbs-Duhem equation. The reality is that thermodynamics involves calculus, as you should know from the last lecture. And as you can see, we've got our thermodynamic identity, which we got from the last lecture, written here. I'll just explain it again. The change in the internal energy of your system is equal to the negative pressure multiplied by the change in the volume. So this means the mechanical energy, the negative of the mechanical energy as applied to the system, plus thermal energy, reversible thermal energy, which is the temperature times the change in the entropy, plus this summation of the chemical potential times the change in the number of molecules. Now, what happens and how do we integrate this equation? So, calculus, you can differentiate, and then at some point you have to integrate so that you can deal with everyday quantities. Now you can see that this is not the easiest thing to integrate, since what do you integrate against? Do you do it against volume? Do you do it against entropy? Or do you do it against the number of molecules? Fortunately, this thing can be integrated with something called Euler's homogeneous function theorem. Now, I'm not going to derive it here. I'll instead just show you the result. which is actually quite a nice result. It says that the internal energy of a system is equal to minus PV plus TS plus the sum of all chemical potentials mu times the number of moles, N. I'm now just going to take a quick detour to introduce you to summations. You've now seen it a couple of times. You may not be aware exactly how they function. They're actually quite simple to understand. What is this big sigma? Because this is the Greek letter sigma, or the capital of it, the capital for sigma. What is this thing? And all it is, it denotes a sum. And I'll just show you by example. Say I want to add all the integer numbers from 1 to 10. You can do this the long way, as I've written here. You can go 1 plus 2 plus 3 up to plus 10, and that is equal to 55. However, instead of taking such a long written piece, you can condense it using the summation sign. And so here is an example. We have what it says, we're going to do a sum, sigma, of all integers, which often is denoted as n. And what you've got is this little subscript I. And what it's just going to say, and to understand what this I is, you have to refer back to the sum. And what it says is I starts at 1, and then it continues to n equals 10, which is what you put at the top. And so n, where I is equal to 1, n becomes 1. When I is equal to 2, n is 2, because n refers to the number of integers, and that's equal to 55. Now, I don't want you to get confused. The n that I'm using here is for integers. It does not refer to number of moles, as I'm going to use in the rest of the lecture. So this is purely for example. All right, I mentioned Euler's homogeneous function theorem. Euler theory is Leonhard Euler, and it rhymes with boiler. Born in 1707, died in 1783, and personally he's my favorite mathematician, and probably the most prolific of all mathematicians out there. He did so much work that he was publishing papers decades after his death, and he did half his work blind. And people to this day are still collating his work into volumes since about 1915. And he's quite famous for what was known as the Basel problem. Look it up. Man, frankly, the guy was just a genius out of this world. All right, let's get back to our Gibbs-Duhem equation. So, we have, from Euler's homogeneous function, integrated the thermodynamic identity, and here it is again. And what we'll do is we'll now differentiate it again. Well, u becomes du, and it's equal to, and this is where we apply the product rule for PV, minus P dV and V dP. So remember, we are using the product rule here. We are going to now apply the product rule again, but now to the TS part of our equation. TdS plus SdT, and we're going to do it again, the product rule to the summation. All right, so now this thing is not our thermodynamic identity, you would have noticed. It's closely related, but it is not the same. We will now go back because we know what du is also. It's the thermodynamic identity, and we're just going to do a simple substitution. And now this should be fairly easy. We are going to just eliminate the terms. So let's eliminate the terms. We eliminate the PdV terms. We eliminate the TdS terms. And we eliminate two summations. which leads us to this result. And this equation is the Gibbs-Duhem equation. So burn that into your memory, and it's going to be important because it will help us in our discussions of chemical potential. All right, the Gibbs-Duhem equation. It's a consequence of using calculus on the thermodynamic identity. And there it is. Burn that into your memory because it will become quite useful. Now, here's the quiz, and I'll just read you the question. Assume there are only two substances, A and B, and assume that you are at constant pressure and temperature. The Gibbs-Duhem equation becomes what? And I'll leave that for the next lecture. Thank you very much.